Hello, I would like to welcome you to lecture 19 of 2FH3. We'll discuss in this lecture Ampere's law and its applications, and this will cover chapter 7, pages 293 to 300 of the book of Sadiq. We discussed in the previous lecture Biot-Savart's law, and I explained to you that Biot-Savart's law is very similar to Coulomb's law in electrostatics because it allows you to determine the magnetic field resulting from a small element of wire. Here we take our knowledge of magnetostatic one step further, and we talk about Ampere's circuital law. And this law is very similar to Gauss' law in electrostatics. We have seen in the previous lecture that if you have a current flowing in a certain direction, then the magnetic field will circulate around that current. And as a general statement of this phenomenon, we have Ampere's law, which is saying that the integration of H dot dl around any closed contour gives you the current enclosed by that contour. I mentioned before in my lecture that if you have a contour which looks something like this, then there are infinite number of surfaces that are surrounded by that contour, not a single surface. You can get the planar surface, which is this one. You can get something like a hemisphere, which is this one, a more elongated surface. You can get infinite number of surfaces. So if you have a current going through that surface, it's flowing through that surface, then if you carry out an integral of J dot dl around that closed contour, this must be equal to the total current flowing through that surface. And remember, the total current flowing through a surface is nothing but the integral over that surface of J dot ds, where J is the current density in Ampere per meter squared. So this is very similar to what we said before in Gauss' law. The integral of d dot ds over a closed surface gave us a charge enclosed. Now the integral of H dot dl over a closed contour will give us a current enclosed by that contour. And of course we observe the right hand rule. The circulation, the direction, the assumed positive direction of the current is in the direction of progress of a right hand screw, and whose rotation direction of the contour. This has to be observed also in this case for Ampere's law. So we already explained to you Ampere's law. The integral of H dot dl is equal to the current enclosed, but this is called the Ampere's law in the integral form. And as I explained to you earlier about Maxwell's equations have integral form and differential form. Here we can derive the differential form in a very similar way. The integral of H dot dl over a closed contour by Stokes theorem is equal to the integral over any closed surface S of curl H dot ds. But if we carry out this one here is equal by Ampere's law to the current enclosed. But this current enclosed will be an integral over the same enclosed surface S of J dot ds. So if you take a look at these two integrals, this one here and this one here, you will notice that we are carrying out two surface integrals over the same surface, and the result will have to be the same regardless of this surface, because there are infinite number of surfaces that is surrounded by this contour L. So this will be only possible if curl H at every point in space is equal to J, to the electric current density. So this is called the differential form of Ampere's law. So Ampere's law have two forms. An integral form, the integral of H dot dl is equal to the current enclosed. The second one is a differential form, which is curl H is equal to J. So at every point in space, if you find the curl of H, this will give you the value of the current density at that point in space. So the magnetic field in general is not conservative. Electric field had a curl of 0. Electrostatic field has a curl of 0 because we say that electric field is a conservative field, a rotational field, while magnetic field circulates and rotates around the current creating it. So curl H is always equal to J, and as we agreed earlier, curl H is a measure of the circulation at one point. So now we know there is an integral form of Ampere's law, there is a differential form of Ampere's law. As an example on Ampere's law, let's consider this case. We have here a magnetic field intensity, and it's given a certain region in space by this formula here. So we have this formula here. And would like to find the current density formula, current density expression. So G would like to find J at every point in this region, and would like to find the total current passing through the surface Z equal to 4, X between 1 and 2, Y between 3 and 5. So this looks like a square. It's a square. It has a length of 1 in the X direction, it has a length of 2 in the Y direction, and it is in the plane Z equal to 4, which is parallel to the XY plane. So it's a square parallel to the XY plane and the plane Z equal to 4. And would like to find the current flowing in the Z direction using two different ways. So in the first one to think about here, how to get the current if I know the magnetic field intensity. We agreed from Ampere's law in the differential form that curl of H is equal to J. So what you have to do, you have to take the curl of this expression, and this will give you the current at every point in space that's created that magnetic field. So we can say that curl H is equal to J to solve for J. Now once I have J, I can integrate J over this square, and when I do this integral, this will give me a current in the Z direction, because the unit normal to the area of this square is in the Z direction. I'll keep Z fixed at 4. So carrying out the integral of J will give me one possible way of calculating the current. The second one is to apply the Ampere's law. I will simply integrate H dot dl around the contour surrounding this area, and this should give me exactly the same answer. So let's proceed now with the solution, see how it's gonna go. So for the first part, I know the magnetic field intensity H. I want to get J, the current density. Then J by definition is equal to curl of H. This is from Ampere's law in differential form. So we write the expression for the curl: Ax, Ay, Az, partial x, partial y, partial z. And then we bought the three components we have for H. H does not have an x component, it has a y component, and it has a z component. So now we take the x component. The x component will give me the derivative of this one relative to y minus the derivative of this one relative to z. This derivative will give us 0. This derivative will give us minus 2 over z cubed x plus 2y, but I have a negative sign here, so this will be the x component. For the y component, this is not a function of x, and this will give you 0, so there is no y component for J. For the z component, if you cross out this line and this column, this row, you get the derivative of this term relative to x, and this will give you 1 over z squared. So now you could see that J has only two components, an x component and a z component. And over the square, remember, we want to calculate the current flowing through a square. It has dimension of 1 in the x direction, dimension 2 in the y dimension, and it's normal, it's Az. Okay, so first we have to find J along that surface and then integrate it. So what we'll have to do, we have to replace every Z in this expression by 4, because this is a square parallel to the xy plane. So at every point on this square, Z is equal to 4, and this y, you put here 4, you get 16 here, you put here 4, you get 64, but you cancel with 2, then you get 32. So this is J that will be integrated over that surface. And remember, because we are integrating J dot ds, and ds here in the Z direction, the x component does not really contribute any current through that square. It's only the Z component. So we'll be integrating 1 over 16 over the area. X will change from its value here from 1 to 2, and y will change from 3 to 5. And this will give us the total current. So to get the total current flowing through this square, which has a unit normal in Z direction, we integrate Jz dot dx dy Az. This is ds in the Z direction, and this will give us 1 over 16 dx dy. Of course, the integrand is not a function of x or y, so this will give us 1 by 2, so the answer is 1 over 8 amperes. But we know also from Ampere's law in the integral form that the current flowing through that surface here, flowing out from that surface, can also be calculated by carrying out a line integral around the surrounding contour, and the right hand rule has to be observed, correct? They have to be observed. So here, if you carry out a line integral around this contour of h dot dl, this should give me exactly the same value of the current flowing through that surface surrounded by that contour, so the surface of this square. Remember, h does not have an x component, and this line integral has 4 segments. One along x, one along y, another one along minus x, another one along minus y. So because there is no hx, when you multiply h dot dl here, which dx, this one will give me 0 contribution, and this one will give 0 contribution. And the reason for that is that there is no hx. So what will multiply dx here will give you 0. Only this integral, the one in the y direction and the other one in the minus y direction, will have a value. So we'll be integrating hy dy from 3 to 5, and here we'll keep x at equal to 2, because along this segment x is equal to 2. And then we'll integrate here again hy dy, but we'll integrate it from 5 to 3. Remember, I don't say it's minus dy, it is dy, but the bounds are from 5 to 3, and along that integral I will keep x fixed at 1. So this will give me 2 values for this closed line integral. So we carry out the 2 segments that are not zeroed over segment 2 and segment 4. Here I integrated from 3 to 5, I replaced every x by 2. And here I integrated from 5 to 3, I replaced every x by 1. And remember, I am integrating here h. So this is hy and this is hy. If you reverse the order of the integrand, you'll see that this term 2y over 16 will cancel with this term 2y over 16. This will give me 2 over 16 minus 1 over 16. So you end up here with 1 over 16. So the integral will be from 3 to 5 of 1 over 16 dy, which is equal to 1 over 8 ampere, which is exactly the same result we obtained by integrating the current J through that surface. So now we know we can calculate the current flowing through a certain surface through 2 ways. Either you carry out a surface integral of the current density, or you carry out a line integral around the enclosing contour of the magnetic field intensity. And this, of course, this is a physical interpretation of Stokes theorem that we discussed earlier in vector analysis. Ampere's law is used in the same way like Gauss' law to calculate magnetic field in problems with high degree of symmetry. If you remember, when we talked about Gauss' law, we said that the integral over d dot ds, if we select the right Gaussian surface, then d will be constant on that surface. So this integral becomes the integral of d ds, and d of course will be not in the same direction as ds, and then I can take d out from the integral. Then this becomes the integral of d multiplied by ds, and this will give us d multiplied by the area of the Gaussian surface. Something similar will happen here. We select something, we call it Amperian contour. So when we carry out this integral here, we carry it over a special path, we call it the Amperian contour, Amperian path. Over this contour, h is constant, and it's either 0, so it does not give me any contribution, or constant and in the same direction as dl. So h dot dl will give me a scalar hdl, and because h is a constant, I can take it out, and then the integral of h dot dl now becomes the integral of h, it becomes h multiplied by the integral of dl, and the integral of dl over a closed contour gives the length of this contour, L. This is pretty much what we have here. Here we had d multiplied by surface area. And this, of course, is equal to the current enclosed by this contour. So the magnetic field in this case is equal to the current enclosed divided by the contour length L. So now we could see that the same way we applied Gauss' law for electrostatics, we can apply Ampere's law for magnetostatics for problems with high degree of symmetry. To give an example on the application of Ampere's law in such problems with high degree of symmetry, let's take a look first at the case of an infinite wire carrying current. Of course, there's nothing infinite. Usually, it's a long enough wire, but we are calculating the field at a distance small relative to the length of the wire. So the wire can be considered pretty much to be an infinite in that case. In that case, if we have an infinite wire, we know that the magnetic field circulates around the electric field. So the magnetic field must be in the phi direction, and the magnetic field will become weaker as we go away from the wire. So it will be only a function of rho. So, but using these two informations, we select an Amperian path, Amperian contour, which looks like a circle, whose center is on this wire here. As a result, when we carry out the integral of h dot dl, h is in the phi direction, so it's h phi a phi. dl here along this contour is equal to rho d phi a phi, so this is dl. And this, of course, is equal to any current flowing through that surface. Because h phi here is assumed to be constant, because it's a constant rho surface, and phi h is only a function of rho, I can take h phi out from this integral, because I'm integrating over a circle which has a closed rho, so rho h is the same over every point here. I can take it out, and then the integral of rho d phi, when I carry out this integral, will give me 2 by rho. When I integrate over a circle, it will give me 2 by rho. And this will be equal to the current enclosed I, or the magnetic field is equal to I over 2 by rho ampere per meter. This is exactly the same result that we got using the Biot-Savart's law by carrying out a complicated integral. So we could see the assumption of symmetry here, or the symmetry of the problem, that we know the magnetic field is in the phi direction, must be circulating around the current, and it's only a function of rho. It decays as you go away from the wire. This allowed me to use the right Amperian path in which h phi is constant. I was able to take it out from the integral and then multiply by the length of the integral, which is a length of the contour, which is 2 by rho, and this simplified things a lot. Another interesting application for this Ampere's law is to calculate the magnetic field resulting from a thick conductor carrying a current. So we have here a conductor which has a radius of A. It's carrying a current flowing into the page. So the current is flowing into the page, and you assume for now it's uniformly distributed along the cross section. Of course, I can give you problems where the current is not uniformly distributed. So you have in that case taken into account the variation of J. But here we assume that the current I is uniformly flowing into the page. And we would like to calculate the magnetic field both inside the wire and outside the wire. And we did something similar. This example is very similar to the case of a charged sphere charged with free charges. Remember, if we talked about that, you have to take a Gaussian surface inside the sphere and the Gaussian surface outside the sphere to determine the electric field everywhere. Now, from the symmetry of the problem, because we know the magnetic field encircles the current, the magnetic field will be in the phi direction, okay, both inside and outside the wire. And we know it will have only dependence on rho. So as you move in the rho direction, then h will change. So if I select a constant rho contour like this one, which is a circle, then h is going to be a constant over that contour. And this is one of the needed properties of the Gaussian surface. So in that case, I can start to apply Gauss law, Ampere's law. But before I do that, I have first to get the current density. The current density here is equal to the current multiplied by divided by the area, and I did that because I assume it's uniform current. The area of this cross section is by a squared, and the current is flowing into the page, which is assumed to be the z direction. So the current is in the z direction. It's an ampere per meter squared. Now, if you apply Ampere's law, we say that the integral of h dot dl over the closed contour is equal to the current enclosed, which is the integral of j dot ds over the surface enclosed by that contour. Because h is constant, I can take it out from the integral, and the integral of dl over this contour will give me the length of this contour, which is 2 by rho. So this is what we have here. Now, if the contour inside the wire, then the current flowing through the surface enclosed by this contour is part of the total current. So it's equal to J dot ds integrated over this area. But because J does not depend on rho, I can simply multiply J by this small area, which is by rho squared. Remember, the area here is function of rho. So if you do that, this is J multiplied by rho squared. We have here rho. Pi will cancel with pi, rho will cancel with rho squared, and you get this expression for H phi. So for every point inside the wire, if you determine its distance from the origin, you can see that the current, the magnetic field increases when rho is increasing. So from here to here, the magnetic field is increasing. It's getting stronger. It's in the phi direction, but it gets stronger as it encloses more current. So it's really increasing with rho. It's I rho over this expression here. So this is what we have, and remember here what I did, I replaced J by I over pi a squared. So this is why I got another pi in this term here. So now we have the magnetic field inside the wire, and we know that it does increase with rho, and its units is ampere per meter. Now if I draw an Amperian path or Amperian contour outside the wire, the enclosed current does not depend on the length of this contour, because the enclosed current is a total current, which is I. So in that case, I don't have to say it's J by rho squared, as simply equal to I, the total current flowing through that wire. What will be increasing is only the diameter of this Amperian path. So for any contour outside, you apply the same rule. The integral of H dot dl is equal to the current enclosed. This is the integral of H dot dl is equal to H phi multiplied by 2 by rho. We took H phi out of the integral because it's constant. The current enclosed is I. It's independent of the length of the contour as long as rho is greater than A. So now we can simply say that H phi is equal to I over 2 by rho, and you see that the magnetic field starts to decay as you go outside the wire. And this field plot here shows you what's happening. The magnetic field is in the phi direction. It is 0 here. It starts to become stronger as you move towards the wire. It reaches its peak on the surface of the wire, okay, and then it starts to decrease again. You can see here these areas are becoming more blue or green, which is indication the field is getting weaker. So the field is strongest here, and then it gets weaker. So if you try to draw it, it's growing linearly with rho until you reach the surface of the wire, and then it's decaying as 1 over rho as you go outside this thick wire. So you can see here, we're able to solve a problem like this because of the high degree of symmetry, and that allowed the application of Ampere's law. If we try to use the Biot-Savart law, it have been way more complicated, and we have had to do lots of integrals to get the same result. Let's see an example on this thick wire thing. We have here a solid conductor of circular cross section that has a radius of 1 millimeter, and here the conductor is along the z-axis. It's carrying a current along the z-axis of 20 ampere. We would like to find the magnetic field at 0.5 millimeters, so at the halfway inside the wire, 0.8 millimeter, a little bit closer to the surface of the wire. And here I'm writing it at 1, but I think this one should be 1.1. I think this is a typo. This should be 1.1 millimeters. So it's just outside the wire. So the wire has a radius of 1, but this one should be 1.1 millimeters. So I will apply the same approach, the one we did earlier. We assume no one told us otherwise, so we'll assume that the current to be uniformly distributed in the cross section. We have 20 amperes flowing in this area, which is by A squared, and A here is 10 to the minus 3, it's 1 millimeter. Then we know that the current intensity is 20 by 10 to the power 6 over pi ampere per meter squared. Now for rho equal to 0.5 millimeter, we apply Ampere's law. Then H dot dl will give me H phi multiplied by 2 by rho. The integral of J dot ds will give me J multiplied by ds, and if you try to draw one of these contours here, the radius here is rho, and rho is variable, then in that case the area is by rho squared, and we know what is J. So if we divide both sides, you cancel pi with pi, divide cancel rows with rho squared, then you end up with h phi j rho over 2. We already know what is j, is 20 10 to the power 6 over 2 pi. We know what is rho. For the first case it's half millimeter, so it is 5 10 to the minus 4. If you simplify all this, you'll see that h phi, the magnetic field at half millimeter, is 1592 ampere per meter, 1592 ampere per meter. We repeat exactly the same steps for the 0.8 millimeter and 1.1. For the 0.8 millimeter, you are still inside the wire, so the same expression we had earlier still applies. H phi is equal to j rho over 2. This is j, 20 10 to the power 6 over 2 pi. Rho in this case is 8 10 to the minus 4, and this will give you 2548 ampere per meter. And you can see the magnetic field is increasing as you approach the 1 millimeter. As you can see, the magnetic field is increasing as you approach the 1 millimeter radius of the wire. Now for the last part, when you consider the case of 1.1 millimeter, you apply still Ampere's law. The integral of h dot dl is equal to the current enclosed, but the current enclosed does not depend on rho anymore. It is equal to the total current. So h phi multiplied by 2 by rho is equal to I. I is equal to 20 ampere, and 2 by rho, 2 by multiplied by 1.1 millimeter, which is 11 10 to the minus 4. If you simplify that, you get 2893 ampere per meter. So the field increased up to a peak at the radius of 1 millimeter, and then started to drop after that. And we don't know, by the way, what is the peak, because we did not calculate the field at 1 millimeter exactly. But it's obviously increased in a linear way. So I can try to do that. It increased in a linear way and then started to drop at 1 over rho as we go outside the wire.